Well, I'm on record. Let me thank Indian Institute of Science again. And it's a pleasure to visit there after getting my master's from the Institute 30 plus years ago. Sandeep reminded me I'm dating myself, but I cannot hide. So this is a completely different topic from what I tortured you with in terms of modified log-Sokolov inequalities, entropy, decay, and so on. So this is more probabilistic combinatorics and with some motivation from theory of computing. My main areas of research are C, P, and C, combinatorics, probability, and computing. And so this addresses two of those, or maybe all three. Okay, so this is a new model, sort of newish model that was brought to us as in participants of a workshop at the American Institute of Mathematics, which used to be in Palo Alto, now in San Jose. David Gamarnik and Madhusudan were the ones that mentioned the model to us, but as it turned out, as we came to find out, people in random graph theory were considering similar things independently. So what's the story? So the whole lecture is going to be focused on G and 1/2, the infamous Taylor-Schreiner random graph with just the simplest edge probability 1/2. Of course, after the lecture, you can hopefully solve several open problems on this model and then G and P and so on. There's lots of interesting things to look at. So ground zero is everybody who's taken the basic probabilistic combinatorics class might have seen, knows that in G and 1/2, the largest clique, largest complete subgraph which has all possible edges inside, is of size 2 log n. Since I bothered to put the constant 2, I must mention the log is log base 2. Okay, so maybe I should say, how many people know this fact? I was told that's the right way to ask the question. You're never supposed to say, who doesn't know this? Nobody likes to admit, by the way, I don't know. So maybe let me just briefly say, because it's super easy. So the first thing you will learn in week number 1 in a course in random graphs or advanced course in combinatorics is the so-called first and second moment methods. Okay, it's just computing the first moment expectation of some random variable. The second moment is computing the second moment as well. And they're useful based on the following simple observation. If you have a non-negative random variable, and in combinatorics, we assume it's, in fact, integer value random variable. So the first moment method is simply using the observation that probability it's positive can be upper bounded by expectation, always, and for non-negative random variable. And if you want to show probability that x is positive goes to 0, it's sufficient to bound expectation, show that goes to 0. The second one, so based on adjusting the parameters, you would like to say actually the probability x positive goes to 1. Right? Of course, we all know if expectation goes to infinity, it doesn't necessarily mean that it happens with probability, positive probability or probability going to 1. So the second moment says, if you can show probability x is 0 goes to 0, which is the same as showing probability x positive goes to 1, and this you can hope to show by using by Chebyshev, there's a simple inequality. You can put the square here or outside. Both versions are true. So in cases where you're able to show the variance, so you first show expectation goes to infinity, a necessary condition by this, and then you show, however, variance is, say, little o of as whatever is your input parameter. Then this goes to 0 as n or whatever is going to infinity, so you get that this goes to 1. As something goes to infinity. Right? So this is the basic vanilla first and second moments. So if you use x to be x sub k, which is the number of cliques of size k, this integer valued random variable, and compute. So you want to identify, question? I just want to show x is for the clique number or in general usually? So I know x is non-negative. I just want to, so I want to show this goes to 0. That's fine. I just want to claim x positive goes to 1. Yeah, that's all right. 5 is more than 1, what I want. Because, so for me, the random variable x is going to be the number of cliques of the appropriate size k. Okay? So now what we do is we figure out what k star is. So k star is going to be the critical value. So you usually choose k star so that expected value of cliques of that size is roughly 1, is a constant. Right? Notice that this is going to decrease if I increase k star. It's less likely. If I step away one or two values from it, then it's going to go to infinity and so on. So this, in the case of this particular random variable, is going to be its expectation. So let me just, So this is, there are this many choices, and because I'm in Gn1/2, this is 2 to the minus k star choose 2. I want every one of those edges to be present. Right? So this now we say, when is this roughly 1? So we can just use some simple, let me drop the star, minus k square over 2 to be roughly 1, which means this is roughly that. So figure out this. So that gives you, taking logs, k is 2 log n minus 2 log k plus 2 log e, something like that. And we identify, right, as usual, the first order term is 2 log n. So if I plug back into this, that gives me the 2 log n. So certainly 2 log n is the first you identify easily. So as I said, you do this calculation to figure out where to pivot yourself. And then if you go up a little bit, it's easy to show the expectation goes to 0. You back up by 1. So there's a very strong concentration result known that's attributed to, I think, David Matula from Southern Methodist University in 1976 or so, and Bolabash also did shortly after. So it's known very precisely. It's 2 log n minus 2 log n plus 2 log e minus 1 or something, asymptotically almost surely. Meaning for every epsilon positive, the fact that the clique number is within 1 plus or minus epsilon of that goes to 1 as in goes to infinite. Okay, so so I decided to spend a couple of minutes on it because we're going to use this fact several times, the 2 log n. Okay, so, and what's been a challenge in theory of computing and other topics, even statistical physics, people came up with various algorithms to try and find such a clique. Okay, now we know that we can establish in 10 minutes. The second part is a little more complicated because you need to bound the variance and so on. Okay? But we know 2 log n exists, and it's easy and sort of trivial to find a clique of size log n, just by greedy. You choose a vertex. On average, there are n over 2 vertices that are neighbors, n over 2 not. Keep the neighbors, remove the non-neighbors. Keep going. So n over 2, n over 4, you last log n. Okay, so log n by this greedy procedure or whatever is easy. Nobody knows how to do better, efficiently. 1 plus epsilon log n for some concrete epsilon positive is none. No polynomial term algorithm. Okay, with decent probability. Say probability more than a half or whatever. So this Karp, I guess, raised it officially at some point. And then people spent a bunch of time working on a so-called planted clique model. This was useful sometimes for cryptographic and other purposes. You start with Gn 1/2, or start with a planted clique of size k for some k. K could depend on n, k a function of n. And then throw in Gn 1/2 on the rest of the graph. Okay, so I do that and I give you the graph. Of course, I won't show you where I planted the clique. Your job is to find the clique. Okay, we know in Gn 1/2 the largest is 2 log n. You would think if I plant something that's log square n size, maybe you can find it somehow. The best known is root n, turns out. I put a much larger, massive clique, then there are spectral and other algorithms that find it. Little of root n is an open problem. And under some statistical query model, this and that, there is even some indications of hardness. Okay? So this was the state of affairs until these two gentlemen said, it's such a mathematician's thing to do in a sense. He said, well, or an information theoretic thing to do. Let's forget about efficiency. Change the model a little bit and ask, can we do better if we measure cost, not in time, some other way? Okay? So again, information theoretically, this should be possible because 2 log n is the largest, so planted bigger, but efficient only. Okay, so get rid of that usual standard one, but instead say you can only look at a small part of the graph. In which way? Query pairs of vertices. Okay, you got to point to pairs of vertices. Is there an edge there or not? So the part you haven't queried is still random, right, on the appropriate number of vertices and so on. And you're given a budget. Of course, if I let you query n squared, then it's easy. Okay? So we're going to limit it. Let's say Q is going to be a function of n. And the question is, what's the largest clique you can find? Yeah, as I said, once we submitted it to a journal, the random structures and algorithms, we got feedback saying we won the first ones, or they won the first ones to raise the model. So there was some work on, typically on sparse random graphs in terms of Hamilton's height, other combinatorial structures. So there's still lots of problems one can think about here. All right. So in the talk, I think most of the slides talk about Q being n, or order n, linear number of queries. Okay, but in our paper, we look at n to the delta for delta strictly less than 2, and at least 1. Why strictly less than 2? Because if I allow you delta equals to 2, that's n squared. You can query all possible edges, and since I don't forbid you, right, from computationally, you can do anything you want. So you can find a clique. Why delta at least 1? Well, if I do Q queries, the most number of vertices they touch is 2Q. Right? If no two queries share a point, like a matching, 2Q. So if 2Q is less than n, if it's less than linear, then you have n minus 2Q that were never touched. So you might as well forget about it. And which 2Q vertices doesn't matter because we're in a Gn 1/2. They're all symmetric, right? So you might as well assume you have at least linear number of queries. Otherwise, you're tying your hand too much. Okay, so that's the setting. And now for any such delta, you can talk about what's the largest fraction between, say, 1 and 2 log n that you can find. Because it's a random instance, we want to find with high probability, or we say, okay, all the talk is going to be at the level of expectations, and we're just going to ask for the probability, say, bigger than a half, rather than probability going to 1 or anything fancy. Okay? And we know, because I haven't, so there's no planted business here. So we know the alpha star is at most 2 by what I said at the start. And we know greedy finds log n. So if you do exhaustive search, you could do, why is this? Well, I'm limited by Q queries, so I choose square root Q, let's say, square root Q vertices, square root Q choose 2. That's Q square root. So roughly, I go to square root Q, and on that, random graph restricted to that has a size 2 log square root Q, right? So that gives me, if Q is n to the delta, Q is n to the delta, then this is 2 cancels with the square root, I get delta log n, okay? So in particular, if delta is 1, then I get log n is exhaustive, but if delta is larger, I could do that. That's something. Turns out if you combine the two, you could do a bit better. This is not so surprising. So basically, so for this, the argument is, so combine the two, as in, so the trivial log n algorithm that I mentioned at the start, choose a vertex, discard all its non-neighbors, keep the n over 2 and keep going. So you can say that the strategy is going to be do that greedy until square root Q remain, and then follow exhaustive. Okay, so mix and match. And we could do the computation. So why log n over, this part is clear, right? Because we just talked about that. Once you have square root Q remaining, exhaustive on that gives me 2 log square root Q. Why this? Well, how long does the process go on? I start with n vertices, n over 2, n over 4, n over 2 to the k, and I stop until this is square root Q, right? I said I stop until what you have remaining is this. But that means n over square root Q is 2 to the k, right? By then, we have found k vertices. So what is k? So k vertices, and that's the size of the clique. So k is log n over square root Q. Yes? So that's a part I found. And then in the remaining, whatever clique I, so together. Okay, is that clear? So easy now. So if delta equals 1, meaning we're in the linear probe case, I'm given only linear number of probes, okay, up to some constant order n. This would be 3/2 log n. Everybody convinced, right? And there's no cheating, right? My arithmetic is extremely suspicious, but I think this is okay. This is the best we know. This is already an open problem to do better than 3/2 log n. I can give you a different way to do 3/2 log n, but we don't know how to do more than. Okay? So it's kind of embarrassing. So we ended up showing this. And the upper bound, so it approaches 2. So I'll tell you what the, I mean, you might be tempted to clap your hands at this point, but we changed the model a little bit more so we could do something else. Okay? So, but for this problem, this is it. And I heard recently that a student of Jacob Fox, and I don't know, maybe Jacob Fox and others, there may be a group of young guys who show this is strictly less than 2, but I haven't seen it yet. It's probably true, but I mean, our result, we have an upper bound that, you know, it's, for a constant number of rounds, it's less than 2, but if you're given more than a constant number of rounds, we couldn't rule out 2, but apparently there's a proof in the making that will show less than 2. It's an open problem. Right, as I said, as I warned you, so we introduced, right, this is, so at this workshop, very nice workshop, Amir Dembo, Nike-san, and others organized at AIM, they made up a list of 10 problems, and the 30 people assembled were asked to sign up which problem they wanted to work on. And the ones that got 5 or fewer votes were erased, and then we had to re-vote to join the surviving problems. And then the rule was after each day you could switch camps. You say, okay, this is a hopeless problem, I'm going to cut my loss. So the 5 authors on this, and we stayed honest to our task, and we stayed with that problem. We let actually one person come in, and she didn't want to join on the papers, and she joined us too late, she thought. But the point of my story was that after day 1, we said, okay, we still have 4 days, we have to do something. They're feeding us. So we introduced, okay, it started with one of the young guys. I forgot to mention my co-authors, Mickey Ratz and Joe Neiman, in particular, the younger guys, Gamarnik and Uri Feige and myself. One of the young guys said, we were told 3/2 log n was possible. That's what we were told at this. Right? And then we were trying to figure out, and one of them figured out that actually he could do in 3 rounds. So the new model is, it could still be n to the delta, or delta equals 1, linear number of queries, but it's adaptive in rounds. So in round 1, you ask a whole bunch, you look at the decisions, go to round 2, ask another, and so on. Okay? So the 3/2 log n I mentioned, we can achieve in 3 rounds, a batch of probes in each. If I give you 4 rounds, maybe you can do better, we didn't know how to. With 2 rounds, we could only do 4/3 log n. And our general upper bound for L, for every fixed L, the number of rounds, the L rounds, unfortunately, if you plug in our upper bound for L equals to 2 and L equals to 3, it doesn't rule out that 3 rounds is more powerful than 2 rounds. So the upper bound for 2 rounds for us is not less than 3/2 log n. While we know we could do 4/3 log n with 2 rounds, we cannot show that you cannot do 3/2 or better. So that's, as I said, there's lots of problems. This is sort of the first of our attempt. So alpha star delta comma L now is the largest alpha, so that alpha log n is the size of clique you can find, while making only n to the delta adaptive queries, and these queries you could do in L round. If you're thinking L as fixed, right, as I indicated, because I don't know how to be smarter with L4 or higher, you can think of L as a constant. So you can think in each round you have n to the delta at your disposal, because we're only talking about big O of n to the delta, okay? That's that. Any questions at this point? Nothing complicated so far. Even the algorithms are simple. The complicated, non-trivial stuff is in the upper bound result. 5 or 6 or 7 pages of the proof. That's the main, okay, in our paper. Okay, so this is clear because in the first one there was no limit of number of rounds, etc. Yeah. So what we could rule out is that if you say L is a constant, then our upper bound does give that you're strictly below 2. While you know 2 log n exists with constant number of rounds, where in each round you're given, say, only linear number of queries or n to delta queries, or some delta strictly less than 2, you cannot touch what you know exists. That, at least, I think this is a decent result. And this is the hard part in the paper. Yeah, we have some, who was it? Eric Moulins was saying, we shouldn't show numerics in this audience. But these are actually, rigorous numerics. These are not some, none of us ran any of these algorithms. These are, you compute an upper bound. As you'll see, there's some optimization involved, min-max types of thing. And if you choose some test function, it gives you an upper bound. And so such rigorous mathematics gave for 2 rounds, 4/3. But you see this number, we tried, at least for a day at AIM, to try and make this below 1.5. That would have distinguished 2 round versus 3 round. But we couldn't. Okay, so there's some, again, you see there's nothing on the left-hand side of 4 and any other higher numbers. So maybe somebody here tomorrow morning will tell me. Yeah, so for delta equals 1 upper bound we have is 2 to the 1 minus 1 over 2 to the L minus 1. Okay? Oh, one thing where the only place where we have an equality, by the way, is not just 1, 1, but if it's alpha star delta comma 1, meaning you have n to the delta adaptive queries, but 1 round, it turns out it's equal to delta. If you're just given 1 shot, ask all the probes in 1 round, you can show delta log n is the most you can find. And that works out nicely for delta between 1 and 2. Because if delta over 2, you know, you could do 2 log n. Delta over 1 is the old result, log n. In between, it interpolates, delta log n. All right, so here's, I mentioned this already, 3 round more powerful than 2. Okay, so in 1 round, as I said, with the square root Q algorithm, just pick, clique is the best strategy. Pick root and vertices and then just score. Turns out that's all we can. So 2 rounds. Now I'm going to show you the 4/3 log n algorithm, okay? Which is better than the just carp 76 log n. So of course these exponents are optimized after you come up with the strategy. So first choose a subset S of n to the 1/6 size and query everybody inside. Okay? In the same round, also ask for this versus the rest. So probe all within S, all between S and T. Okay? Now what's the largest size clique in S you'll find? Well, use the formula 2 log n. 2 log of this, that's 1/3 log n. Okay? Again, everything at the level of expectation because we just want decent probability for the algorithm. Now, observe that T prime now identified. So we asked everything between S and T in round 1. So T prime are the vertices in T which are connected to everybody in S prime. So if you pick somebody in T, what's the chance they're connected to everybody in S prime? Well, the size of S prime is what? 1/3 log n. So 1/2 raised to 1/3 log n. Right? Every one of those edges is there. That's the probability. 1/3 raised to 1/2 log n. And by expectation, How many such there are? There are n to the 5, 6. So that gives you this. Again, this is just at the level of expectation. There are n to 5 over 6 guys here. Probability each one is connected to everybody in S prime is this, 2 to the 1/3 log n, which is root n. Which means, on average, n to root n vertices here are joint to everybody in S prime. We're not saying they're joint to each other or anything. That's round 2. Okay. So in round 1, you do these questions and do the math, and then probe everybody inside T. So again, by the 2 log whatever result, 2 log root n means. So you find a 3rd log n here, a log n in the yellow, together, because everybody in T prime is joined to everyone in S prime. Yellow and green together form a clique of size 4/3 log n. So you might have thought about it. Actually, as I was preparing for this some time ago, as I was going over 2 rounds, I was thinking, why did I query everybody between S and T? Why didn't I just do some? But then I realized I was doing a 3-round algorithm. So in 3 rounds, that's what I did. Sorry, let me go back. In 3 rounds, you pick one of the statements in my previous, this one, probe all between blah, blah, and move it down. So first ask about S. You identify, now it's not n to the 1/6, but n to 1/4, because we optimize the parameter. So you find half log n here. Now ask between only S prime and T. Before we asked between S and T in the same first round. That's the only distinction. Ask between S prime and T. By the same math, probability anybody here joined to everyone in half log n is 2 to the 1/2, right? 1/2 is this. But now you only took n to the quarter away. So there's n minus n to the quarter. So let's say n over log n. Why n over log n? Why am I choosing only n over log n? Well, what am I doing with them? I'm going to query between S prime and T. How many edges are between S prime and T? S prime has half log n. S prime has log n, so I can only do n over log n. So the number of queries is linear. So this is the algorithm where delta is 1. You can repeat it for any delta, same procedure. You get a result that's more general. Sorry? Yeah. I forget which one. I wrote it somewhere, but those depend on delta. I think, the 3/2 log n becomes 1 plus delta over 2. Yeah. If I remember, the 3 round becomes 1 plus. So delta equals 1 is the case sometimes. Otherwise, if you have n to the delta queries, but I would have to cheat and look at how S and T prime depend on delta. I don't remember. Okay, so ask between, because you know S prime has size log n, you can only do n over log n. So together the number of edges is order n, which is the constraint. Yeah, in the 3rd you look to find this yellow subset. Probe all pairs within T prime. Okay, T prime has size root n, that's fine. Root n choose 2 is linear in n. But you will find 2 log root n, that's log n, okay? So half log n, this is half log n, that's log n. Yeah. Now we run out of algorithms. Nothing more we know how to do. Okay, this part is quite technical. Let me at least try to give some idea. So again, this is first moment plus graph theory, combinatorics type stuff. And this is, whoa, okay. Yeah, so we fix, say, the alpha log and target size, right? So we want to show somehow it's unlikely to find a clique of size alpha log n for alpha something, right? Alpha, this alpha star delta comma L. and you have L rounds. So the beta fractions, these are betas are fractions, they are variables to indicate how you might have conducted your queries over L rounds. Okay? You ask some beta 1 fraction, beta 1 times n, for example, and then so on. And basically, our observation is that if you had L rounds, in some round you must have made significant progress. Okay, and we want to focus and bound the probability of that, how likely, unlikely. For that, we say, okay, round I is significant, the number of probes to this particular, have one clique in mind, and then we're going to do the expectation, number of cliques of that size or whatever. Up to I minus 1 rounds, you probed only this fraction in terms of the beta, summation j1 to I minus 1 beta j k choose 2. But when you went to the next one, you exceeded that. One is at most, the other one is at least. Okay? And again, by induction, you can show this must have happened, because at the end, if you probed based on this beta, the sum of all betas up to L times k choose 2, there must have been, right? Because why k choose 2? Because that's the size of the clique you supposedly discovered, you output. So those k choose 2 must have been probed somehow. Okay? Now, one point is that you see after round I minus 1, which is defined this way, using this whatever I eligible, I significant set, the probability that what you will discover is going to be a clique is at most 2 to this summation from I to L, because you've only done up to I minus 1. So the rest is still the random graph. So the probability that will turn out to be a clique is exactly the number of edges in there, discarding the I minus 1 stuff, okay? And then this we multiplied. So the reason it's first moment is union bound by how many such k's there are, okay? Now for that, it's not just some simple n choose k or something. It's more complicated. Okay, so this is the probability. The other one is how many. So this was the painful part. But we identified fairly precisely what this number is. If you throw in enough parameters, you can figure out, right? So capital N, little n, m, k, beta is a maximum number of sets of size k that can be beta covered in an n-vertex graph with m edges, okay? This is the thing that we then multiply by the 2 to the minus summation j I to L, beta j, right, in the previous, k choose 2. Beta covered means number of edges in the induced subgraph at least beta fraction of total possible. Because that's the computation we were left with in the first moment method before. Given a certain number of vertices, certain number of edges, and now this is the total, and then now subsets of size k. These are cliques. If beta covered, then how many such sets do I have? Okay, I'll say, hopefully, a word or two about how we get this bound, but proving this theorem is the bulk of the paper, about 5 pages or whatever. Okay, there's some extremality involved. It turns out there's going to be a clique and a bunch of isolated vertices, or a clique and an independent set, like here, but each of these is joined to everybody in the clique. Okay, turns out and that part is actually 3 of the 5 pages of the proof of this so-called complete spectrum. Where is this coming from? Have people seen anything like this? Galai-Edmonds decomposition theorem. Okay, this is famous Jeff Edmonds and Tibor Galai, Hungarian, both famous people in matching theory. So Tutt's theorem is something most people might have heard of. Hall's theorem, I hope yes. Tutt's theorem, many should say yes. Tutt's theorem is a criterion that tells you when in a graph you have a perfect matching. Perfect matching means a matching independent edges that contains every vertex. So there's a very easy necessary condition, just like for Hall's theorem. Hall's theorem is for perfect matching to exist in a bipartite graph. Tutt's theorem is for general graphs, right? And Tutt's theorem says the following easy observation, that if you have this graph, you remove any subset of vertices S, okay? When you remove this, suppose you have a bunch of odd components. Odd component means the number of vertices in each of these is odd, okay? So you remove this and you're left, what that means is these guys must be joined only to S. These are disconnected components. If there was an edge between these two, then they would be the same component, right? You have only this. So for you to have a perfect matching, what must happen? These guys are odd in size. So there's like 3 of them or 5 of them, right? So you could match most of it, but at least one should be left unmatched. Then you cannot partner everybody inside. So each of these guys needs a partner from S, right? So that means size of S should be at least K, the number of odd components, yes? Because if you had fewer here and you created more odd guys, there's no way you can match them up. This is an easy observation. It's one of the theorems that a graph theory book calls Tonkas for the only necessary condition is also sufficient. So it turns out, so Tutt's theorem says for every S, every subset S, if you have this property, meaning you're not dead, then actually you have a perfect match. It doesn't give you an algorithm. That's a complicated story. But in the quest to come up with an algorithm, Edmonds and others identified what's called Edmonds-Gallai theorem, which is more complicated to say, but Edmonds-Gallai theorem talks about the structure of a graph for a maximum matching. Maybe there's no perfect matching, but you have a matching of certain size, and it gives a characterization into 3 types of vertices. Turns out these even vertices, odd vertices, and then neither. So there's a corresponding characterization. What's the connection to this? I don't think I have a slide on that now. So the connection is you can bound n little m k beta by something else. You make up another quantity. I need to check this. No. I forget. Let me look. So my notation, what is capital M K beta? Let me make sure I did it right. Oh, sorry about that. Right. So, yes, this is, K should appear somewhere. Okay. This guy, so we identify, what we say is, if you query beta times K choose 2 edges, okay, then in those edges, there must be a matching of a certain size. Right? There's a whole bunch of edges. We cannot hope to understand how those edges that were probed. But we define this mk beta, which is over the minimum over all graphs on k vertices with beta times k choose 2 edges, the maximum matching size. Okay, you want to get your hands on the maximum matching size. over a class of graph. So you don't know anything except the size of how many vertices were touched. Let's say that's K. Over all possible such graphs, what's the smallest the maximum matching can be? Okay. Once you define that quantity, you can say, oh, if M edges were queried of this, then if there are M edges, there are this many ways to choose the matching, and then of the N vertices, K minus 2, because these matching edges are covered here, 2 times that, and the remaining is K. Okay. So anyway, the point is, we make up this other parameter that involves matching. So if you touched a certain number of vertices, you must have given rise to at least this size of maximum matching. And that's how we upper bound this capital N. And then there's a 2-page proof of bounding capital M K beta very precisely, thanks to Gala-Edmonds theorem. So the Gala-Edmonds decomposition comes once we go to the maximum matching stuff. Okay, that's kind of a high-level idea. Yeah, and these are pretty tight, at least they're tight up to K to the K, where K is like log N. So the last slide, this is my last slide, and then open problems. This I have nothing to do with. Why am I showing you? So Mickey Ratz and his student, just recently, they took this further. I motivated the whole problem by saying nobody can find better than a log N, while 2 log N exists. There's also the planted clique model. So what Mickey and his student did was they took this probe version, planted a clique besides the 2 log N, and then said, okay, now can you find planted? And for this one, actually, they more or less understand up to logarithmic terms in the bounds. Right? So there's n square over k square. If you do fewer than this, no hope. If you do n square over k square times log square n, then yes, we can find, or at least detect. So they have 3 results. Basically, that's recovery possible, detection possible, but recovery impossible, and detection impossible. Let's say for any k, if you do n square over k square or fewer than that, you cannot find. When k is more than 2 log n, 2 plus epsilon log n, when it's at least information theoretically possible, they say if it's n square over k square times log square n, they can find it. Sorry, no, n square over k square log square n plus some linear n, whatever, n log n kind of, then they can find it. Otherwise, they can detect it but not find it. Yeah, so the phase diagram is this pretty much complete. And the open questions, again, as I said, this might have been solved. We'll probably know if it appears on the archive, but still, I doubt whether they know precisely what it is. And in the Mickey and his students' paper, how to shave off some log factors. And this is a nice question. Is 3 rounds more powerful than 2? Or 4 rounds more powerful? Okay, I'm sorry I went 5 minutes over it.